Right then, so this is 17A. This is the end of 17A. Excuse me, I'm actually doing this after I did the work problems. So just again, I want to remind you guys that you'll have to probably click. This is this is a PowerPoint presentation, which means that every time I click it, unless I can somehow figure out how to make it not do that, then you'll have to click at home. The alternative would be to make a video of this like you would put on YouTube, but I don't want to do that because the file sizes get so gigantic. The one that I just did for 17A work problems was only 100 megs, so I was actually pleasantly surprised at that, but then I cut it short. So this would go along with that one. So this is the end of 17A because remember that we had already finished most of 17A before the big spring break thing happened, and then it got extended and all that. So when we were doing 17A, we had already done titrations, buffers. We had done also some of the actual titrations themselves, like we had done strong acid, strong base, and we had done weak acid, strong base. So what I'm going to do is just the last part, which is the weak base, strong acid. So remember, whenever I click this slide, I'll try to remember to tell you I'm going to click, and that will mean that you'll have to click yours as well. Probably you may have to click it a couple of times to get it to move. Otherwise, you'll just sit there. So anyway, when we get done with this last section, there's another section in your slides that I send you as a PDF, right, that talks about weak acid, weak base titrations, which I specifically said are very difficult to do, so we're going to skip that. And all the textbooks do that. And then also there's a section on polyprotic acids that we're not going to do. I put it in there so that if you're pre-med or whatever, that you can look it over, but we're not going to go through that. So I'm not going to even have, I don't even have that in here. So what I have in front of me now that I'm going to go through is a very abridged version of that chapter's PDF. And then there's also a little bit of stuff at the very end that deals with indicators that we're not going to get through. So I'm going to try to wrap this up in about a half an hour. And so what we're going to do is we're going to go through these same 4 steps that we did for the other 2 main kinds of titrations. That's before we start. So that would be when you only have the weak base. You haven't added any of your HCl or whatever. You just have the weak base. In that case, you use your Kb for your base. And you just figure out what the concentration is if you're not told it already. And then you go ahead and do your calculation with an AS table to figure out what the pH would be. But remember, for a weak base, you're going to wind up with POH first. And then you subtract that from 14, right? And then the second step, what they do in this set is they do it halfway to the equivalence point. But you have to be aware that it doesn't have to necessarily be halfway to the equivalence point if you're in that buffer range. If you're in that range between the initial start point and the equivalence point, you could be, they could give you that on a final exam anywhere in that range. So it's really not a good idea just to learn, this little shortcut formula that if I'm halfway to the equivalence point, it's pH equals pKa. So we'll talk about that. We'll talk about how to be able to do it at any point in that range. But just to bring to your remembrance, if you're in that buffer range, we call it, between the start point and the equivalence point, then you're in the buffer range, which means you can use the HH equation as long as you remember that when you use that, you're looking for pKa. Be careful with that. So that's why this one is a little confusing. This third titration with weak base strong acid is confusing because everything is backwards or upside down. So instead of using Ka, for example, we have to use Kb. So like if we write a base plus water gives the conjugate acid plus OH minus across the top of our ice tables, then we have to remember to use Kb there. And so when you're doing the HH equation with this, you have to do the same thing. Remember, when you use the HH equation, it's not pH equals pKb. It's pH equals pKa plus the log of the base over the acid. So if you're given Kb, what do you have to do to get to Ka? Well, you have to divide 1 times 10 to the minus 14th by whatever the Kb is. And just as one example, for ammonia, it would be 1.8 times 10 to the minus 5th, which for some weird coincidence happens to be the same number as the Ka. We've mentioned this before, right, for acetic acid. And then the third step is at the equivalence point, which again, that's always the hardest one. So at the equivalence point, the weak base you started with, like if it was, for example, NH3, has all been eaten up and converted to NH4+, and also all of the acid that you're adding, the HCl or the HNO3 or whatever, the strong acid, is all eaten up. When it eats up the weak base, or when the weak base eats up the strong acid, they produce, in doing that, they produce whatever the conjugate acid is of the weak base that you started with. So if you started with NH3, then what you've done is if you took 0.1 mole of NH3 and you've gotten to the point where you've added 0.1 mole of the HCl, then that means you're at the equivalence point, right? It also means that you've now eaten up the HCl and you've eaten up the NH3, but you haven't eaten up everything with acid-base properties, because you've also produced 0.1 mole of the NH4+, which is the acid. It's the ammonium ion, which is the acid form of NH3. So at the equivalence point, I'm kind of going through the whole thing here. At the equivalence point, what you would do is figure out the concentration of the NH4+, and then you want to write that reacting with the only other thing in the solution at that point, right? What's the only other thing in there? Water. So you say, okay, then NH4+ plus water on the left is your reactants, and then the double-headed arrow, and then that's going to produce H3O plus NH3. That would be the thing that you would write across the top of your ice table. And then in order to be able to finish the ice table, you're going to have to know the concentration of NH4+. Now, in the example I just mentioned, the concentration of the NH4+ initially would be 0.1 moles, which is how many moles you produced of it, divided by whatever the total volume was, right? So, for example, if you started with 100 milliliters of your weak base and added 100 milliliters of HCl, what's your total volume? Well, it's going to be 200 milliliters. But you want to convert that to liters, so it would be 0.2 liters. So your concentration initially of your NH4+ would be 0.1 moles divided by 0.2 liters, which it seems like that should be 0.5 molar. But whatever it is, then you put that at the top in your I row. Remember, it's an ice table, so in the I row you put whatever the concentration is, and then just finish your ice table. But that's the hardest step. So that's the one that you should probably pay attention to the most, because if you get asked that, you don't want to be sitting there trying to remember how the heck do I do this. And then the last step is the inverse of what we did when we did weak acid strong base. The last step means you're past the equivalence point. In this case, what that means is you started off, let's say, with 0.1 mole of your weak base, and you've added more than that of your strong acid. So you have an excess of strong acid. So in some ways, this is actually very easy to do. You just, for example, if you've started out with 0.1 moles of your weak base and you've added 0.15 moles of the strong acid, then how many extra moles do you have left over of the strong acid? Well, you have 0.05 moles left over. So figure out the concentration. In other words, take the 0.05 moles, divide it by the total volume to get the concentration of your H plus or H3O plus, and then just take minus the log of that and you're finished. So it's like, again, the inverse of what we did on the last step for the weak acid strong base. All right, so having said all of that, we've introduced it. Now I'm going to click Remember, if it doesn't move right about now, then you'll need to click on the slideshow. So here we go. So I'm going to also go ahead and keep clicking here. So I'm going to click again and again. And here we are. Okay, so the titration, so this is the last one you'll be glad to hear that we're actually going to do. The titration of a weak base by strong acid, reading just across the top here, and let me get my marker working. Here we go. So before any HCl is added, we just do this problem the same way we have with any weak base problem. We want to set up an ice table, remembering that we're going to set the ice table at equilibrium. The things at the bottom, we're going to set them equal to Kb, not Ka. So what we need to know here is that this is 0.05 molar NH3. We'll need to know this part over here later for the second, third, and fourth step, but not now. All we need now is the concentration of our weak base, which in this case is NH3. Well, that's good because NH3 is easy to work with because it's got a nice, easy number to remember for its Kb. So all we have to do is set up an ice table. We don't have any stoichiometric calculations to do, right, because we haven't added anything. We will do that later, but not now. So we want to set up an ice table. The initial concentration of the NH3 will be 0.05. So what do we write across the top of our ice table? Well, we're starting obviously with NH3, so we would write NH3 plus something. And what's the same thing we always add to either the weak acid or the weak base? That's supposed to be a 3 plus H2O, double-headed arrow. Use your imagination. Double-headed arrow. Okay, now tell me what, let me go back and try to fix this a little bit, if I can. That's a little better. All right. Now tell me what's going to happen to the NH3 when it reacts with water. In other words, what am I going to write right here and right here? So think about that for a second. Well, this is a base, right? So it's going to pluck a proton off the water, and it's going to turn in from NH3 to NH4 plus. NH4 plus. And what is that going to leave water as? If it loses a proton, it will leave that as OH minus. All right, this is what's going to go across the top of your ice table. What are we going to write under these? For the initial, I. I is initial. I'm trying to fix my chair and do this at the same time. Under the NH3, what would you write? So before I tell you, what would you write? Just look at it. Do you know? Are we told that? Yeah, we're told that in the problem statement, right? It's the concentration initially, which is what? 0.05, right? So that would go here under the row that says I, right? And then here we don't worry about the water. It's just we neglect it. And then under the NH4 here in the first row, and also here, what do we write? We write 0, right? Because we're assuming that we're starting with 0. So where did I get the 0.05 that I'm going to put right here? It's from right here. It was given to us. So again, notice that we don't really care at this point about the 100 milliliters because it doesn't matter, because all we care about is the concentration, which is probably a little counterintuitive, or maybe it just sounds like it shouldn't be that way, but it is. But before we go any further, why don't we go ahead and figure out how many moles we have of NH3. So we need to know the volume for that. We don't need it for this problem, but we will later. So let's go ahead and do it now. So to get the number of moles, we multiply the volume, which in this case is 100 milliliters right here. But I'm going to change that to 0.1 liters. And then we're going to multiply that. I'm not going to write the L. We're going to write, here goes my parakeets again, so hold on for a second. Cover them back up. 0.05. I let them get uncovered for a few minutes while I was taking a break, and I forgot to cover them back up. And those of you who have no idea what I'm talking about, I've got a whole bunch of birds in my room. And when I was doing the work problems earlier for this chapter, I mean, they were going hog wild. So I covered them up, and that seemed to work. All right, anyway, so 0.1 liters here is the volume and 0.05 moles per liter. Okay, and I also put away my calculator. So I'm going to try to do this one-handed. So I'm going to go ahead and multiply this out. 0.1 times 0.05. And I know what it is, but I just want to make sure. So it's 0.005 0.005. And what is that? When you multiply liters times moles per liter, you get moles, right? So we don't need it, as I said, now, but we'll need it later. So we're starting off with this many moles of the NH3, which I'll try to remember this. It's 0.005 moles. But for this problem, we don't need it. So we just go ahead and make our equilibrium expression, which we write across the top of our ice table. So our ice table will wind up being down here like this. And I mean, I'm going to show you that later in the next slide or whatever, but I just want to do it now before we go over there. Ice. So this one here. Oh, and then here, this would be, we didn't write this, or I didn't write this. So this is going to be 0.05. And everything else would be 0. Right? Skip H2O, and then this is going to be 0 and 0. And then this is going to be plus X. So I'm not going to write this all out, but this would be plus X here. And so would the OH minus. And then everything I'm writing for NH4 plus will be the same for the OH minus. So we'll have X here and X here. And what are we going to have over here on the left-hand side? 0.05 minus X, which we're going to write as just 0.05. And forget about the X. Assume it's negligible. And we're going to wind up with X times X here and here. I'm at the bottom. X times X divided by 0.05 equals what? So try to remember what it's going to equal, which I'm sure most of you do. It's Kb, right? And do you remember what Kb is for NH3? It's the same as the Ka for acetic acid. It's 1.8 times 10 to the minus 5th. So you could do this, and you really could just do this in your head, right? Well, maybe not in your head, but anyway. Okay, so what's the equation going to be? It's going to be x squared over 0.05 equals, and then it's going to equal 1.8 times 10 to the minus 5th. Solve for x, and when you do that, you're solving for this, but more importantly, we really don't care about that. We're solving also for this, and this is what we care about right here, because that's the concentration, or well, it's the what we're looking for the OH minus here. It's the concentration of the OH minus. So if we take minus the log of whatever we end up with down here, then we will get the POH, right, which we will then subtract from 14 to get pH. All right, so I'm going to skip on to the next slide. And it didn't work, so I'm going to hit N. Okay, so I'm not sure what's going on. I don't know if you can even hear me now. This thing is kind of messing up. So anyway, I'm going to go ahead and keep going. I'm going to hit next slide. Finally. Okay, so this is what we mentioned. We wound up here with 0.05 x and x, and we're going to set x squared over 0.05 equals kb. Here. All right, so hopefully this is becoming very familiar to you. Hopefully you understand this. So we solve it for x, then we say, okay, what is x? Well, when we solve for x, we get that x here is this number. Well, what is that? Well, so look back at your chart. It's this. It's the concentration of OH minus here. So if I take minus the log of this, I'm going to get the POH. But we don't want that. So we want to find the POH, and then when we find that, what do we have to do then? We have to subtract it from 14 to get the pH. Okay, so that's it. That's it for the first step. So I'm going to go ahead now and click to the next slide. All right, so now it gets a little harder. After 25 milliliters of 0.1 molar solution of HCl are added. So what we'll have to do is multiply this number, but we want to change it to 0.025 liters and multiply that times 0.1 moles per liter to get the number of moles of HCl we've added. Now, we're going to assume here that it's less than the number of moles we started with of the NH3 because we haven't even done any steps yet, so we're basically going to assume that we're in that first range, which is the buffering range, where it's kind of flat, like in other words this part right here before we get to the part where it goes up and goes over the curve. I mean, here would be the equivalence point. So we're going to assume that we're in this range right here. So when we're in this range between the start point and the equivalence point right in here, then we can use the HH equation if we want to. All right, so, or we can do it the other way that we've been doing it, which would mean that we would figure out what the concentration is of the NH3 and the NH4 plus, and then basically, to be honest with you, it winds up being the same thing. It's just a different way of approaching it. All right, so here we had 0.1 times 0.05. So for the NH3, we have 0.005 moles. It's 0.005 moles. And that is for the NH3. That's what we started with. That's the base, the weak base. How many moles did we add of this? Well, 0.025 times 0.1 is 0.0025. I'll come back in a second and put in that decimal. All right, so 0.0025 moles of HCl were added. That's less than the amount of base we started with. So this is the HCl. It's 0.0025. Okay. So we started with 0.005 moles of NH3, and we've now added half as much acid. In other words, we're halfway to the equivalence point. Remember and keep this in mind that when we do this, what's going to happen? Well, the best acid adds to the best base. And it's clear here that this is the best acid here, and that this is the best base. So you really don't have to rack your brain trying to figure out which one of these is going to react with the other. It's going to be the NH3 and the HCl. So a lot of the stuff that they put in the slides is kind of like stuff that you would want to do just to be extra careful. But on a final exam, you're not going to have time to go through. You just want to pick out what's the best acid, what's the best base, and then react those things together until you run out of one of them. In this case, the HCl is going to run out here first because you have less of it. You've only got half as much of it. But while it's reacting with this NH3, it's producing a third entity. And what is that third entity? What is the HCl producing when it reacts with NH3? NH4 plus. So that's going to end up over on the right-hand side over here somewhere. It is going to be in the last column, and that's what we're producing when we react this. This HCl here starts off at 0.0025 moles and goes to 0 because it's eaten all up. And this one starts off at 0.005 moles and goes down to 0.0025 moles because the other 0.025 moles were eaten up when the HCl reacted with it, and now over here we have 0.0025 moles of the NH4 plus, which I'm going to run out of room here, so I'm going to have to put it in the second row down here, 0.025. Now there are two different ways you can approach this. So let me write this up at the top. This is the NH4 plus. Okay, there's nothing mysterious about this once you kind of figure out what is going on here. You just have to do this a few times and it starts to click, hopefully. So what we're saying is that we have 0.0025 moles of NH3 that are left over, but we also produce the same number of moles of NH4. So we're halfway to the equivalence point, and so when we do, for example, the HH equation, we would say pH is pKa plus the log of this thing right here, this thing over here. It doesn't really matter. In this case, it would ordinarily, but over this. But since they're the same, these two numbers are the same here. When you divide one by the other, you get 1, and the log of 1 is 0. So you end up with pH equals pKa. So why don't we write that? There aren't that many slides, so maybe we can get away with it this time. So pH equals pKa. It's just like pulling teeth to try to do this. pKa. Okay, so what's pKa? Well, it's the minus the log of the Ka. What's the Ka? And what are we going to find it for? Well, we want the Ka for the acid, which in this case is NH4 plus. What is the Ka for that acid? Well, we have to take 1 times 10 to the minus 14th and divide it by the Kb for NH3. One times 10 to the minus 14 divided by 1.8 times 10 to the minus 5th. And I'll just do that real quick, so bear with me for a second. I'm going to just do this 1 times 10 to the minus 14th divided by 1.8 times 10 to the minus 5th. And I'm getting 5.56 times 10 to the minus 10th. Okay, so the pKa is 5.56 times 10 to the minus 10th. So what's the pH? 5.56 times 10 to the minus 10th. Okay, does that make sense? It's a very basic solution if that's the case, right? Does that make sense that it would be basic? Yeah, because we've still got more base left. We've still got NH3 left over and the acid is all gone. So that is the answer to this part. So we've done part 2. We'll go ahead and flip the slide now. And for some reason this thing isn't working. Okay, and I'm going to flip it again. So here's the stoichiometric calculations. We had to do this first. So we just reacted the best base with the best acid. We had more of the base, so we had a little bit of it left over. And every time, and we had none of the acid left over because there was less of it. And every time one of these reacted with one of these, it produced one of these. next, next, next. Okay, excuse me. So for both of these, since we're halfway to the equivalence point, we wind up with the same number of moles and also the same number of liters. So to get this 0.125 liters, you would add how many milliliters you added of the acid, to however many you had of the base when you started. And in this case, it was 125 total, which we convert to 0.125 liters. Okay, so I think hopefully everybody understands that. So divide the number of moles by the number of liters to get the concentration. And now you can go to your ice table, but you really don't have to do that. You can use the HH equation. Next slide. If you do an ice table, you're going to get the same thing. This is going to be 0.02, and that came from the previous slide. Same thing here. So down at the bottom we have 0.02 plus x, which we neglect the x. 0.02 minus x, again we neglect the x. So we have 0.02 times x divided by 0.02, which you can see that 0.02 divided by 0.02 is 1, so we just wind up with x equals Ka, so whatever the Ka is for that. Again, be careful, it's not the Kb, it's the Ka. So it's not 1.8 times 10 to the minus fifth like it would be if you were using the Kb for NH3. Next slide. So to get the pH, we found that the x equals, pH equals pKa. The x is 5.6 times 10 to the minus 10th, which is just the Ka, and then the pKa will be minus the log of this number, which is 9.25. And we're finished. Right, so what happens if you don't have a situation where you're exactly halfway? Well, in that case, you can do it the way we did it here, but you're not going to have exactly these same numbers. They're not going to be the same. The closer you are to the equivalence point, then the more you're going to have converted of the base to the NH4 plus acid. So the numbers are going to get, the concentrations will get less, and then the opposite thing would happen. The point being, the main point is that you're not going to wind up with the same numbers here and here. But you can still do it that way. You just neglect this x. So it's just like we've done in the past, and this one. And then, so for example, if this were 0.03, instead of 0.02, and this one were 0.01 instead of 0.02, then you would have 3 divided by 1 here, which would be 3x equals 5.6 times 10 to the minus 10. Or you can also use the HH equation, but to do that, you'll just have to figure out what the concentration is of your acid, your weak acid conjugate, and your weak base. And then divide the concentration of the base by the acid's concentration. So you can do anything in the range from the very beginning point here to the equivalence point here. Anything from here to here, you can do the way that we just did this, or you can use the HH equation. Right, all right, now we're at the hard part, which is the equivalence point. So what that's going to mean is that the acid that we're adding has eaten up all of the NH3, and also the NH3 is eating up all the acid, right? So there's no more acid. So here, at this point right here, there's no more acid and there's no more base, the original base, the NH3. So the HCl and the NH3 are all gone. There's no more HCl and there's no more NH3. But what is left? Well, what's left would be what we make when we react NH3 with HCl. What do we make when we react them together? The H comes off, goes onto the NH3 and makes NH4+. So it actually turns out that that's the only thing that's around at this point, NH4+. And then there's one other thing, and that's always available, and that's water. So, I mean, and I talked about this also in your work problems, but what you're going to have to do at the equivalence point when you're doing a weak base strong acid is you want to write this across the top of your ice table as NH4+, and of course plus water. It's always plus water. Double-headed arrow. And then this H plus will go under the water and make H3O plus. I know this has to be frustrating for you guys. Plus NH3. Okay, but we don't have any NH3 right now, right, because it's been eaten all up, but we will have a little bit of it after this NH4+ starts to react again with the water. All right, so this is going to go across the top of your ice table. This is really the key to when you're at the equivalence point. When you're at this equivalence point right here, you're not going to have any more of your NH3 or your HCl. You're just going to have this stuff right here. So you have to figure out what the concentration is of that. So if you're at the equivalence point, what that means is that you've had the same number of moles of acid as you had of base originally. So that's going to be the same number of moles that you're going to have of the NH4+, because every time 1 mole of NH3 reacts with 1 mole of HCl, produces 1 mole of NH4+. So that number of moles divided by whatever is now the total volume. For example, if you started with 100 milliliters of the base and added 100 milliliters of the acid, now you've got 200 milliliters total, so, or 0.2 liters, so you just divide. Then when you do that, you get the concentration of the NH4+. So if, for example, if it were whatever number, then you just write that here. And what are you going to write over here, right here, or here? And the answer is 0, right? And then this one here would be 0 plus x is x. 0 plus x is x here. And over here, whatever you get would be whatever you got minus x. And then you set that equal to Ka for NH4+. And that would be 5.6 times 10 to the minus 10th. All right, I'm going to go to the next slide. So at the equivalence point is what we just talked about. So we started off with 0.05 moles of NH3. We've already mentioned this before, 0.05 moles of NH3, right? So if we're at the equivalence point, that means that we've added 0.005 moles of the acid. Okay, these concentrations weren't the same, so we wouldn't have the same volumes of the acid and the base, but we know how much the total volume is because they told us that we had 100 milliliters of the base at the beginning and they've added 50 milliliters of the acid. So we have a total of 100 plus 50 is 150 milliliters or 0.15 liters. So that's going to be our total volume. The only thing left over at this point is going to be the NH4 plus, 0.15 liters. And we're going to have this many moles here, 0.005 moles, because that's how many moles we had of the NH3 to start with, and so that's also how many moles of HCl would have to be added. So we have this many moles of NH4 plus divided by the total volume of 0.15 liters. Next slide. Next. I'm having a really hard time getting this thing to go. Okay, so here's what we end up with. We actually just figured this out on the previous slide that we did. We end up with 0.005 moles of the NH4 plus. Next slide. Next slide. And we divide that by the total volume of 0.15 liters. And when we do that division, we get 0.0333 molar for the NH4 plus. So this is what we're going to write in the I row under NH4 plus. Next slide. Here. So for initial, this will be 0.0333, and this will be 0, and this will be 0. So 0 plus x is x, 0 plus x is x, and this is 0.033 minus 6. So we're going to end up with whatever Ka is for NH4 plus, which is 5.56 times 10 to the minus 10th, equals x times x divided by 0.0333. Solve for x. When we solve for x, we look back over here to see what x stands for, and it stands for H3O plus, which means we're in good shape because we take whatever we got for x, we take minus the log of that, and we have the pH, and we're finished. Next slide. So when we do that calculation, we should get x as 4.32 times 10 to the minus 6th. And when we take minus the log of that, we get 5.36, and we're done. Okay, so again, just to remind you, this is the hardest one, so just keep at it. You'll get it. You just have to do a couple of extra things for this one that you don't have to do for the other ones. Okay, so the only thing left is we have to do after the equivalence point, and in this particular set of titrations, what we're meaning by that is that we've added more acid. So we have an excess of acid. So all we have to do is subtract how many moles we started with of the base, which we already know that it was, I think it was 0.05. We subtract that, whatever the number was, we subtract it from the number that we've added of moles of acid, and that will give us the excess acid, number of moles, and then again divide that by the new total volume, which will now be different. So next slide. So here we've added 0.06 liters of 0.1, so that's going to be 0.006 moles of acid we've added, and we added it to I guess it was 0.005 moles of the base. So we have 0.001 moles, I believe, and let me flip to the next slide. Yes, 0.001 moles left over of the H plus after it's all reacted with the NH3, which is now gone. Okay, so again, we always have to make this caveat here, or this warning, that you're gonna, when you're taking the test, it's possible you're gonna look over here and say, oh my gosh, I've got, this is an acid, but it's a weak acid, but it's an acid, and I've got 0.005 moles of that. Actually, I have more of this than I have of this. And so again, the explanation here is that we don't care about this because it's a very weak acid. It barely dissociates. So even though we have more of it than we have of the H plus over here, it's such a small factor because it doesn't really dissociate that much. Whereas this completely dissociates. We're considering this to be the H plus that would have come off of HCl, right? We know that when we put HCl in water, it completely dissociates. So this is 0.001 moles of HCl. It's completely dissociated. Whereas this 0.005 moles over here of the NH4 plus will dissociate such a small amount that you might end up with only like 1 times 10 to the 7th moles of H plus coming off of this one. So forget about this one. So this is analogous to what we did for the last step. Remember when we were doing weak acid strong base, right? In that case, we ended up with OH minus, and then we also ended up with acetate. We said that we wanted to forget about the acetate. So if you don't remember that, well, we talked about it in class, and it's not on any of the videos. So, but it's the same thing. It's just that it's the opposite of what we're talking about now. All right. So anyway, the bottom line is that we want to divide the number of moles of H plus by the total volume to get the concentration, and then take minus the log of that, and then we're done. So what's the total volume? Well, we've got 100 milliliters of the base, and we've added 60 milliliters of the acid. That's 160 milliliters total, or 0.16 liters. So we're going to divide this number right here by 0.16 to get the molarity. Bingo, there you go. So 0.16, whatever we get when we divide that, is going to be the molarity. Let me just actually do it real quick. 0.001 divided by 0.16, and I'm getting 0.00625. And then I'm going to go ahead and actually finish this. So the log of that would be minus 2.2, and minus the log would be 2.2. So our pH, I'm going to flip this slide now. And that's correct. So the pH is going to be 2.2. And we're done. Okay, so happily. If you have any questions about this end of the chapter here, or anything else in the chapter or in the work problems, be free, or feel free to email or whatever. And again, this is going to wrap it up for chapter 17A, along with the work problems that I did earlier. So this is all we're going to do for exam 2. Exam 2 will be Wednesday, which is, I believe, the 1st of April. So on the 30th of April, which is a Monday, we'll finish by these videos. So we won't have class, but at some point, either before or during the 1st of April or whatever, you should watch the videos. Go through the PowerPoints, the PDFs, and then on Wednesday, you'll have an online exam 2, which means that you'll just go online, and I'll publish that at a little before 8 o'clock, probably at about 7:45, and you'll have until 11 o'clock to do it. So that will be set. And it will be over chapters 16 and 17A. Just to go ahead and set the stage, after that we'll do 17B, and we'll probably go ahead and do 17B, 19, and maybe 20. It's just going to depend on how things go before we do the next test, and then we'll have to wait and see how it goes. But anyway, so that wraps this up. So if you have questions, please email. I'm going to flip to the slide, and here is the curve for the titration that we just did. This is weak base strong acid. Next slide. Here's a summary of the weak base strong acid titration, the one that we just did. And then here is, next slide, here is a master summary of all 3 titrations, if you want to look at this. And I believe that wraps this up. So that's it. So good luck with this, and we'll see you again in the work problems.